Okay. For example, if I ask you, okay, at a given temperature, draw out the pressure chemical composition plot. You know this is the things I'm asking for. Okay. And the features I'm looking for is actually typically I'll give you what PA star is, what TB star is. Okay. Then I say if this is an ideal solution, how would this look like? I need to draw, okay, this is linear, that is linear, that's your P total. Described in the solution phase. This is the things described in the vapor phase. Okay, and definitely you can label this, okay, if pressure goes higher, then you know this is your, inside your system. This will exist in the liquid form, okay, and below this line is in the vapor form. Okay, so there are many elements I will actually want you to show on this plot. Okay, first thing is actually make sure you label the axis correctly. It's P versus the mole fraction. Second is actually to label the PA, PB star represent the pure, the vapor pressure of pure substance. Third one is actually to show, okay, this ideal solution. So we must show this linear relationship, okay, of each individual and the total vapor pressure, okay. And then you know, if you want to know the chemical composition in the vapor phase, it follows these green lines, okay. And the very last one is to label this. At higher pressure, UX is in the liquid form. At lower pressure, the solution is in the vapor form. All right. So those are the components I will actually look for, and give credits. Okay. If you miss some elements, okay, some credit will disappear. All right. So now the first questions. This is a very important example, okay, and you want to make sure you know this thing fully, okay, it's very important. It's very important. So think about this. If today we control the P external, okay, and we are under equilibrium, we're under equilibrium. Basically, we say if we change the vapor pressures, okay, we'll wait until they reach equilibrium. Okay. So if we start a pressure somewhere here, okay, assuming this is your P external. Okay. If this is your P external. Okay. And then you know in the beginning I say you have a chemical composition of, let's put it somewhere here. Okay, I say you have a solution, you have ideal solution. Okay, where you know your XB is, let's say 0.5 in the beginning. Okay, so at these very high pressures, okay, I will ask you, inside your system, do you have liquid solution or you have a coexistence of liquid and the vapor?
Liquid. Just liquid?
Just liquid, yes. The answer will be just liquid. Okay? Because you're under a very high pressure. Okay, and it's higher than the most volatile components inside your system. Okay? That means you you basically prevent all these molecules escaping to the this area. Okay? So in this case, you don't have actual vapors inside your system. All you have is liquid. Okay? But you can change this P external. Okay? So if I lower down the P external slowly. Point here. Okay, so this is your P external now. Okay, now your B is going to start to evaporate into your system. All right? So you know this is the pressure where your B is going to, if you have a pure B, then you're going to start to have some vapor coming out. Okay? But right now I say your system is actually a mixture of A and B, right? And it's actually 50% each. Then at this point you will still have your solution completely in the liquid form. Okay? Until you keep decrease your vapor pressure up to this point. Okay, so this point is very important. You need to know what this means. Okay, EEXT. So I would suggest you go to your Hangout at page number 3. Okay, so this is the things we are discussing right now. Okay, number 3 and the number 3 is the things we are discussing right now. All right. So when you decrease your vapor pressure up to this point, then you know some of your molecule inside the solution is going to generate some vapor pressure. Okay? And when you keep decreasing this, up to this point, okay, when you go below these points, all your elements will exist in the vapor form. Okay, so here will represent the last drop of your liquid become a vapor. Okay, so let me say it again. So here is the first vapor molecule generation. Okay, and the bottom one here is the last drop of liquid vaporized. All right? So beyond this pressure, if you keep lowering down the pressure, what's going to happen? All your molecules inside your system become vapor. So they'll become a single phase condition. All right? So if you notice, actually, I can ask so many questions. For example, we learned the phase rule, right? So the phase rule says the degree of freedom to describe a system is actually C plus P minus 2, right? This is your phase rule. Okay? So you know, at different vapor pressures, okay, you actually have different phases inside your system. Okay? So I say if you actually at these vapor pressures, okay, you know inside your system all of them exist in the liquid form. Therefore your phase equals to just 1. Okay? But if you are somewhere between these 2 points, you are going to have liquid and vapor coexist. Okay, so in that case the P is going to equal to 2. Okay? But if I go to a pressure that's below these points, then you go back to P equals to 1. Okay? Yeah. So if I say any pressures above these points, your system is going to exist in a single phase. Okay? Therefore, the degrees of freedoms you need to describe the system will equals to, of course, this 2 conformal system, right? So C equals to 2. So it will be equals to 2 plus 1 minus 2, which equals to 1, or the things above this pressure. Alright? But if I am asking about a pressure between these 2 points, but any pressure between these 2 points will make your system exist in a two-phase condition, which means you have your